Cool. It's should be going.
Thanks, Will. So here's a question. How do I mute Slack?
I could just stop sending you messages.
Yeah, I was going to say. There must be a way of actually muting it. I've never thought about this before. Will, do you have any idea?
Quit it.
Well, we can't because I need to do the questions.
No, I know. There is a way.
This is in the preferences.
Let me remind myself. Top right hand corner under your profile. So where you go to like change your display name and whatnot. There is a option called pause notifications, and then it gives you a time to select.
You can mute all sounds.
There we go. There's like a million different ways of doing the same thing, it seems, but notifications are none. Okay, so we've got about 185 people now. So shall we make a start?
Sounds good. All right. Welcome, everybody. Thank you for joining us for the second iteration of SAZERAC, the Summer All-Zoom Epoch of Reionization Astronomy Conference, something that we started last year, very early on in the pandemic, before virtual conferences were now a thing, and now virtual conferences are everywhere. Some are much fancier, I think, than what we put on here, but we do the job of getting us together to hear about the latest research, especially from junior researchers in the field. So SAZERAC has a pretty big SOC, so I'm just going to acknowledge all the help we've had from those folks. That's Caitlin Casey at the University of Texas at Austin, Anson D'Aloisio at UC Riverside, Marusha Bradich, UC Davis, Romil Dave at Edinburgh, Xiaohui Fan at Arizona, Charlotte Mason at Harvard CFA, Pascal Louche at Geneva, Masami Ochi at Tokyo, Laura Pentorici in Rome, Aprajita Verma in Oxford, and then Steve at Sussex and myself.
Thanks, Steve. And just to note that we have a cadre of students who are helping us as a kind of virtual LOC. And I will get a list and I'll credit them all later as well. I just realized I don't have the list of all the students who are helping us this week to hand, but I will sort that out. So I was just going to say, last year, the justification for this conference was obviously to give junior members of our community the opportunity to obviously advertise their own work and network. This was obviously extra important last year because we were one of the first all online conferences and many other conferences were closed. And we felt that last year went so well that we wanted to do this all again. But obviously we still do have the pandemic pressures. I'm not really sure of any conferences that are really going on in person at the moment. So, I mean, I hope things are better across the world. And obviously with the vaccination program kind of speeding up, hopefully we're on the way out. But even with significant levels of vaccination here in the UK, we're now entering a third wave of the pandemic, which is a little bit depressing to hear about. And we've just found out locally that some of our easing of our restrictions is slowing down. So there is still a that there is still the opportunity, there is still the motivation there being a pandemic. Now, I think some of the conversations that we've been having over the last year as well is that there are other reasons why doing at least some conferences online like SAZERAC makes sense, and probably going forward into the future. So we all know that climate change is important, and every little bit helps. So I know there's lots of views out there in the community, but my anticipation is that we're going to go to probably going to have less in-person conferences going forward in the future. And so I think there will always be a place for virtual conferences like this. And again, it's not just the environmental impacts, but in terms of access, obviously SAZERAC is completely free. If you've got caring responsibilities, it's probably easy to manage something like SAZERAC, particularly as we record all of our talks. And there's several other reasons. Now, this year, this is also a really great opportunity this year where we can hear about and plan to work on Webb, because we all now know what Webb is going to observe in its first observing cycle. I was going to make the mistake and say that we all know that Webb is going to launch this year, but I don't think we're quite there to make that definitive statement, although I think we're all very hopeful that we will see a launch in late October or November. And just a note here that the TAC has obviously agreed with us that there's going to be lots of great science that we can do in cycle one. So I think what really surprised me about the results of cycle one was how many large programs have been awarded time, which are going to be really invaluable for doing science. And obviously the whole point of today's session is that we're going to hear about many of those very large programs and about how maybe you can get involved or what data will be out there for you to use in your own analyses. Steve?
Yeah, so we wanted to acknowledge the environment that we were in last summer when SAZERAC happened, not only the pandemic, but also the social justice movement that started in the US that led to the delay of the original SAZERAC conference. While significant strides have been made in many academic circles over the past year to try and make our community more inclusive, more diverse, more equitable, much more work needs to be done. And we encourage our community to continue to vigilantly work on these issues in our field. For anyone who is interested in working on these topics or discussing these topics, there is a diversity, equity, and inclusion related channel. I think it's called topics-DEI. You can find under the channel browser. We encourage you to start and contribute to conversations there.
Great, thanks, Steve. So I'm just going to mention a few logistics. So first of all, and possibly most important, a reminder for you to read and follow the code of conduct. And if anybody wants to contact the SOC about any issue that's been raised, then you can either do that via Slack or directly to our email addresses. There is an SOC-wide email address as well, which is advertised. So if there is an issue, please do tell us as quickly as possible. For speakers, remember that the format is speaking for 10 minutes, followed by about 3 minutes of questioning, and then we'll have about a 2-minute handover. Okay, so we're building in these little gaps just to make sure everything goes very smoothly. All the speakers should be promoted to panelists. And so what we will do is at about 9 minutes for your talk, I'll send you a 1-minute warning just via the chat. But I think the experience last year is actually more so than in person. People were generally very, very good at kind of regulating how long they were speaking for, which is great. The question and answer. So this is where it all becomes a little bit more complicated. So we're not using the Q&A feature in Zoom to do the questions. We decided to do it all via Slack. This is because we've obviously got people joining via YouTube. And by doing it via Slack, that means we're going to have a record of all the questions. And it also means that speakers can answer questions later on, maybe after their talk as well. So it's all in one place. So it's only one place that the chair needs to look for. If you want, okay, so in terms of how you ask a question, if you go to the Slack, you should see separate channels for each of the sessions. And then in each session, there'll be a separate thread for each talk. And so you just ask your questions in the thread. Now, the exception to this is if you want to ask a question anonymously. There should be information about how you ask an anonymous question, but it turns out you can't ask an anonymous question in a thread. You can only ask it in the channel. And so we'll be monitoring the kind of wider channel as well for anonymous questions. Okay. On Slack, you'll see there's a whole range of other channels. So for example, Hire Me, tech support, we have a channel for diversity, equality and inclusion, or equality, diversity and inclusion, depending which side of the pond you're on, education and public outreach. There's also topical channels where if you have a recorded talk or you have a poster and you just want to post something in there, then feel free. We haven't added people automatically to those topical channels. You should be able to add yourself to those topical channels quite easily. So if you're just interested in, for example, 21 centimeter, there should be a relevant channel there. Might not be called 21 centimeter now that I've said that. Okay. If you signed up for the networking opportunity, you should have gotten an email by now. If you haven't, then please contact Charlotte Mason. And the very last thing is we're going to trial a service called WonderMe, which we don't actually have time to trial it now, so I'll trial it at the end of this first session. But this is a way that we can chat with each other socially. So WonderMe is completely free, which is why we've chosen it for SAZERAC, because obviously we're not charging anything. But yeah, I'll give you a demo at the end of these first talks and you can see what it's like. And so I'm going to start off and, sorry, Steve, can you just announce the next talk? I haven't got the schedule open right at the moment.
Yes, I do have it, although I hit it. The first talk is from Jehan Kartaltepe on the Cosmos Web program, and the title is Cosmos Web, the Web Cosmic Origins Survey.
Thanks, Steve.
All right, I just shared my screen. Hopefully everybody can see that. All right, good morning, good afternoon, good evening, everyone, whichever time zone you happen to be in. Thank you all for joining for the first session of this meeting, which I think should be very interesting. And I'm very happy to be starting off the session about JWST because many of us have been spending many, many years thinking about JWST and what we want to do, and really our dream science that will be done with this telescope. And we've spent a good chunk of this pandemic thinking about JWST and writing proposals. And so, I share what Steve said earlier, that I think a lot of us were pleasantly surprised by the results of the TAC and how much extragalactic science really came out of that. I think it's recognized that we need to do a wide variety of surveys early on in the Webb lifetime in order to study all of the things we want to study. So I'm going to kick it off by talking about Cosmos Web, the Webb Cosmic Origin Survey. So this is a survey led by Caitlin Casey and I, along with the Cosmos team. So I'm going to jump right in and give you the details about the survey. I think this is the piece everybody wants to know. What are we going to do and what data will be available? So Cosmos Web is a 208-hour program, and we're going to cover 0.6 degrees with contiguous NIRCam observations in 4 different filters, which are listed here: F115W, 150W, 277W, and 444W. The depth ranging from about 27.5 to 28 magnitudes. In parallel to that, we're going to have MIRI observations in a single filter, F77W, covering 0.2 square degrees. Now, because of the parallel field layout and our prioritization over the NIRCam coverage shown here in blue on this map, the MIRI observations won't be completely contiguous. Instead, the MIRI observations are going to be in stripes across the field, with most of them overlapping with the NIRCam coverage. I think the main thing that we really want to highlight and that I want you all to take away from this talk is that this survey is intended as a community legacy survey, right? Like all of the other large Treasury programs, the raw data will be public immediately, but we're also committed to releasing our data products quickly and efficiently so that the entire community has this data set to start looking at, to start playing with, and to be planning their own follow-up observations in the future. And so this figure highlights our coverage, so 45 by 47 arc minutes in NearCam with the MIRI strips shown in red, and with the candles field overlaid to give you a sense of scale. I think a lot of people are familiar with the candles coverage in Cosmos, so that helps to give you a sense of scale there. All right. So Cosmos Web has three main science goals that we want to accomplish with this data set. The first one here is the one that's most relevant for this conference, and that's to identify thousands of galaxies in the epoch of reionization, spanning from redshift 6 to redshift 11, mapping their spatial distribution. So this is key for a survey like Cosmos Web. The large area contiguous survey allows us to study their environment, quantify their environments and the level of clustering for these EOR sources. And then we can investigate their physical properties relative to the environment with which they're in. The second main science goal is to identify and characterize rare quiescent galaxies in the first 2 gigayears of the universe, so Z greater than 4. And the third is to directly measure how the stellar mass to halo mass relation evolves with redshift out to a redshift of 2.5, and then explore how it varies with certain galaxy properties. And so we're going to spend the most time in this talk talking about the first science goal, of course. And I also want to point out that beyond these three key science projects that our team initially proposed, there's really an infinite amount of science that you can imagine doing with a data set like this. And so we hope that the community will be ready to jump on this as soon as possible. When we planned out this survey, right, the need to have a contiguous area to study the clustering of reionization sources, and for the lensing measurements that we're going to make for the stellar mass to halo mass relation, really led to the Cosmos field being the ideal choice for such a survey. So we needed a large area field that has extensive and near uniform ancillary data. So Cosmos has existing X-ray through radio observations. There's existing HST F814W observations, which are really essential for optimizing our redshift 6 to 7 galaxy selection. There's a large number of UV optical IR bands that already exist in the field that have provided superb photometric redshifts and will really help to leverage the JWST filter set for photometric redshifts at higher redshift. And there is extensive and constantly growing spectroscopic coverage in the field. I think in recent years, the Cosmos field has really become an area that a lot of people have targeted for their own spectroscopic follow-up. And so in parallel to this, another program that we currently have going on is to collect all of that ancillary data, including archival observations that haven't been looked at or published, and put them all in one place for the community to help enable science that can be done with all of that spectroscopy. Cosmos is an equatorial field, which is essential to optimize follow-up. That means every major ground-based telescope on Earth will be able to follow up sources that Cosmos Web identifies. And in particular, accessibility by ALMA was something we felt was really important because we'd like to be able to use ALMA to follow up sources identified by Cosmos Web. And Cosmos has been selected or is likely to be selected as a calibration field for many future projects in future surveys. So this seemed like the ideal place to put a survey like this. I want to point out the complementarity. So in the next few talks, we're going to hear all about different surveys that are going to be done with JWST. And I think it's really important to acknowledge that in cycle 1, James Webb will image several tiers of the extragalactic wedding cake. So in cycle 1, we're going to have immediately at our disposal data spanning large areas to small areas, shallow data, deep data across the entire range, which is very exciting. And in addition, there are many targeted programs looking at specific objects and peer parallel programs, which you'll hear more about. So I want to highlight the depths of Cosmos Web. So this is a magnitude versus observed wavelength plot that shows all the different filters that are currently available in Cosmos. And then in orange are the filters that we're going to cover with Cosmos Web. And so you can see the relative depths of those here to a few different templates. And so surveys like Sears and Primer, the depths would be, at the bottom of this plot, and surveys like JADES and WDEEP are really off the edge of this plot. So this really highlights the complementarity of all of these different surveys in terms of their area coverage, their depth, and their filter coverage. All right, in Cosmos Web, we expect to detect about 4,000 to 5,000 galaxies at redshift 6 to 8. About 70 to 85 of those we expect to have MIRI detections. And then we expect to detect about 500 to 600 galaxies at redshifts 8 to 10. About 10 of those hopefully will have MIRI detections. And we expect to detect 30 to 50 at Z greater than 10. And I want to point out that because of the relative shallow coverage of Cosmos Web, these are all going to be toward the brighter end of the luminosity function. So they're going to be very complementary to the objects that other surveys are going to be finding. But this will allow us to really constrain the bright end of the luminosity function and the stellar mass function to Z greater than 8. The wide area coverage means we can investigate the clustering of these EOR sources. So we're going to construct density maps in several high redshift bins in order to investigate how clustered and how well these sources trace reionization in the early universe. And we expect to spend a lot of time on future follow-up observations. And so the fact that we're going to detect a lot of bright sources will enable efficient follow-up from ground-based telescopes such as Keck in the VLT and from ALMA for spectroscopy. We of course expect that there will be future cycle JWST programs to follow up sources, and as well as future Hubble imaging, and which will allow us to identify Lyman alpha emitters and constrain the physics of these sources, constrain the ionizing photon production, their IgM neutral fraction, their metallicity, their dust content, etc. So all of the details that we're used to studying about low redshift galaxies we'll be able to do for these EOR sources in the future, which will be very exciting. All right, so this diagram shows the area coverage. Sorry, I'm distracted there. On the left here and in the upper right are cosmological in-body simulations showing what we expect to detect from an area like Cosmos Web, which is highlighted in white. And so the pink areas show the ionized hydrogen gas, and the blue areas show the neutral IgM. And so the galaxies we expect to detect with Cosmos Web at our depth are shown by the black dots. And so this shows that the clustering that we expect to see is on the order of the 10 to 40 arc-minute scale. So we need an area of this size in order to detect this level of clustering. In the middle and the bottom here is a reconstruction of taking these mock galaxies and deriving density maps for those to show how well we can actually identify these structures. Okay. I'm not going to spend time on our other two science topics, but feel free to ask questions if you have any. Cosmos Web will detect rare quiescent galaxies at Z greater than 4, and our filter choice was really optimized to separate quiescent systems from dusty star-forming galaxies. So we really expect to be able to constrain the density of high redshift quiescent systems and constrain theoretical models. And finally, we will study the evolution of the stellar mass to halo mass relation by conducting a careful weak lensing analysis in the field. This diagram shows the observed evolution from HST observations in the cosmos field, and we expect to be able to push this out to redshift 2.5, as well as look for variance with properties such as galaxy morphology and color gradients, which will allow us to test various quenching models. So in summary, Cosmos Web will provide a contiguous large area multi-filter data set in cycle 1, which will enable the science I talked about here and many, many other science projects beyond that we hope the community will become involved in. Follow-up observations will be crucial for reionization studies, and we hope that this data set will be invaluable to the public. And I'll end there, and I'm happy to answer any questions.
Thank you very much, Jehan. And remember, if you do have any questions, then please put them in the Slack. We're just going to have a roughly 30-second breather while we give people the opportunity to put questions in. So if you do have any questions, do put them in, and we'll come back to the questions in about 30 seconds. Going to see how awkward these pauses are. We thought they were a good idea.
Jehan, I'll give you the first one. So we have a question that asks, will there be public catalogs with all the ancillary photometry based on a NIRCam source catalog?
Yes, so that is our plan. So we will be, based on our NIRCam data, measuring the photometry and all of our other data and producing a catalog that's matched that way. That might be a little bit longer time scale from some of the initial releases, but that is our plan.
And our next question is, I'm sorry, I'm going to paraphrase this a little bit. Do we have any quasars in this field, particularly at redshifts greater than 6? And
yes, we do.
Do you know how many we have?
I do not know offhand. I would have to look that up. So I'm not sure exactly how many there are, but there are a number of known high Z sources and high Z structures in this area.
Excellent.
Okay, so a good follow-up to that one. Somebody was asking specifically about the protocluster at Redshift 6.9 identified in the logger survey. Do you happen to know if that is included in your area?
Yes, so I believe that one is just slightly off the edge of the area.
Okay.
Yeah.
Right, there is one more question in the chat, but we've just run out of time. So if Jehan, you wouldn't mind answering that one in Slack, that would be great.
And people can continue to ask questions of Jehan and of all the speakers in their respective Slack threads.
Casey, would you like to share your screen?
I sure would. Let's see if I can make this happen. Okay. Today's the first day I'm back in my actual office, so everything's a little bit different. So.
Well, just while you're doing that, I'll introduce you. So our next speaker is Casey Popovich, who's going to tell us about science with the WDEEP survey.
In principle, okay. Okay, I think I'm sharing. Can you see me? Can you hear me? Can you see my screen?
It's all good, yeah. Okay,
great. All right, I'm going to attempt to do some various things. Let's see if that works. All right, well, it's a pleasure to be here to talk about, as Jehan said, James Webb is now on the horizon, and we are adequately, not even, just in awe of what we're about to accomplish with it. And so I want to talk about one of the surveys I'm particularly excited about, which is called the WebDeep Extragalactic Exploratory Public Survey. It's sort of one of those acronyms that we needed to invent, which we call WDEEP. It comes on a logical successor to many other deep fields done by various space telescopes, including the Hubble that we're also familiar with. I want to highlight some key contributions, including Steve Finkelstein, the PI of this program, myself and Nor Perskal, who are co-PIs, and then I'll talk throughout the presentation about some contributions from Jennifer Lotz, Michaela Bagley, Daniela Berg, as well as other members of the WDEEP team. This is truly a collaborative effort on this. But just to jump into it, I want to give a little bit of background, which is there's been a long legacy of just trying to understand what can we learn by going as deep as we possibly can with these telescopes. And thinking about James Webb during the aborted Cycle 1 proposal call a couple of years ago, Jennifer Lotz at the time had this idea of how deep could we go in Cycle 1 with James Webb, primarily because it's a limited lifetime mission. There's unlikely to be any servicing missions. If you're going to go deep, you should do it early just to discover what's actually out there. Whatever we think you're going to discover with James Webb is not what we're going to discover with James Webb. And we'd like to learn as much as we can as early as possible in the mission so that we can then inform ourselves about what to do in later cycles. And so I'm just showing here an image of the Hubble Ultra Deep Field. This is taken from Garth Illingworth's reprocessing of the data into the extreme deep field. Many of us are probably familiar with this data because it allows us then to just see snapshots of the universe as early in time after the Big Bang as we possibly have been able to. And this builds on a legacy then. And maybe many of the people here are probably too young to remember, but the universe in the deep field sense really was discovered in 1995 with the inception of the Hubble Deep Field, which was just when Hubble Space Telescope pointed a blank field of sky to do exactly this, see what is there and just find out what we could actually discover. And at the time, galaxies were then showing up at redshifts 3 and 4, primarily through the Lyman break selection method that many of us are familiar with now. This was then followed on by a successor of various surveys, including the Ultra Deep Field, which you're seeing here again. The ACS component was done in 2004, and that opened up the universe out to redshift of 6. Beyond that, the Lyman break begins to shift, through the optical bands into the infrared, and we need surveys like what was available from with C3 infrared detectors that went on the telescope in 2011, opening up the universe to 7 and 8. I know many of my colleagues think we're now pushing it to 9 and 10. I think that's really the purview of James Webb. And so the inception of this W deep field was to allow in cycle 1 the ability to probe the universe at the deepest redshifts we possibly can, including opening up large samples of galaxies at redshift 10 to study their properties, to understand their contribution to reionization, and then to inform ourselves about what we plan to do in future cycles with the James Webb Space Telescope. And so I'll just illustrate this here. The program for W Deep targets good south, but really focuses on the Hubble Ultra Deep Fields. What you're seeing here in the grayscale is the exposure time available with ACS, the F814, this is the wide eye band imaging. The black and white rectangle is the goods ACS field, and also the candles with C3 field mostly covers that. And then the dashed blue cyan line, the dashed white line in the middle, those are the ultra deep fields proper. Jennifer Lotz, early on, being at a space telescope at the time, was aware of the fact that the deepest I band pointing on the sky exists right in this polygon over here, which I'm shading in green. This has, on the order of 100 hours of Hubble time in the wide eye field, achieving limiting magnitudes with Hubble of magnitude 30 AB, for example. The idea then that Jennifer Lotz had was that you can observe both this parallel field with NIRCam, with James Webb, and the focal plane is such that it places NIRISS, the other infrared imager on James Webb, on the Hubble Ultra Deep Field proper. And so that's illustrated here, where you can place the NIRCam red, the shown in red here, the NIRCam imagers, on this ultra deep ACS field, combined with the NIRISS shown here in magenta that would then overlap with the Hubble Ultra Deep Field. And so then this takes advantage of a couple things. One, it allows James Webb NIRCam to overlap with the deepest I band pointing on the sky available from Hubble. And it allows NIRISS, which has a spectroscopic, Sleepless spectroscopic capability, very similar to what WIF C3 has, but now going all the way through the K band, to overlap with the Hubble Ultra Deep Field, and allows us then to take advantage of the deepest B band imaging on the sky, as well as the other fields, the filters that are available for the Hubble Ultra Deep Field. And so we leverage off the deepest pointings that are available with Hubble, what we can then do an ad for James Webb, for example. And so just to give you a summary, if you're taking screen grabs or trying to write down notes, these are the main goals for WDEEP. There are many science opportunities you can do. These are the primary ones that we're using to motivate the survey. So with NIRISS, and I'll talk about that one a little bit first, where the main focus here is to understand star formation, metal enrichment, and of course then feedback in low mass galaxies. So we can identify emission coming from galaxies at stellar masses less than 10 to the 9 over a wide range of redshifts, sort of cosmic noon pushing toward the early epochs in the universe. And it overlaps with the deepest B band imaging anywhere on the sky. Simultaneously, these are really two surveys in one. NIRCam imaging then overlaps with this deepest I band pointing on the sky and allows for the efficient detection of galaxies beyond redshifts of 10, where we can then study science such as the evolution of the faint end of the UV luminosity function, make observations and constraints on star formation efficiency, and feedback in, I'll say this in quotes, first galaxies. I think we all hope they're first galaxies, but I think we're not naive enough to believe that's the case. And then you can see below the limiting depths, they're actually very well matched. For NIRCam, we leverage off the Hubble imaging that goes down to 30 AB magnitudes in F814W. And we observe it in 6 various NIRCam filters. We all know how that works. And the limiting depths go between AB 30.6 and 30.9, for example, which are just astronomically insane. Simultaneously, that's the NIRCam part, NIRISS then will achieve 5 sigma detections of emission lines down to about 1 to 10 or 10 to the minus 18 in CGS units, all the way from the J band, the H band, and the K band. And we'll get all 3 of those bands. Just to illustrate what that gives you, and I'll show a plot about that in a second. If I focus on an actual image of the B band imaging from the UDF, we're illustrating here in boxes sources that are near the detection limit. These galaxies have magnitudes of 29.5 to 29.7 in the ultra deep field. This is in the B band. All of these, if they're redshift 2, we're achieving UV luminosities of about minus 16 or so, which is a star formation rate about 0.1 solar masses per year from the UV. These galaxies we would be able to detect the H alpha emission from in the NIRISS imaging. And so anything you can see, detect in the B band imaging, we should be able to get a spectrum from it if they're in the right redshift range, of course. But that allows a lot of opportunities to study science, star formation, metal enrichment, et cetera. And I'll talk about some of those. Okay, this is a simulation that Nora Pierscall did in preparation for the survey in NIRISS. It's showing the large image you're seeing here is a snapshot, a small portion of the F115. This is the J band slitless spectroscopy that we expect, built off of the JADES input catalog from Christina Williams and company, where many people are now familiar with how this works, but you get a smearing of each galaxy, and then you can detect the individual emission lines. We will achieve this then very deeply in J, H, and K. This is a simulated spectrum of a galaxy at redshift 2.2 that Nora provided to motivate the proposal, where the stellar mass of this object is 10 to the 7.7. So we're achieving masses that we just would not be seeing feasible from any telescope we currently know about at these redshifts. And the H alpha flux here is 10 to the minus 17. And because we'll cover all 3 of these pass bands, F115, F150, and F200, this allows us then to do a lot of various scientific studies, both for star formation and for metal enrichment. And of course, I talk too much, so I'm going to move through this a little fast. But these are the emission line features we'll be able to cover, including the Balmer decrement from redshift 1 to redshift 2 in a bit. That allows us to study dust and star formation in those galaxies. And then we can study, we'll have oxygen 2, oxygen 3, and H beta for various metal enrichment type studies from redshift 2 out to 3.5, almost redshift 4, for example. I'm going to skip over some of these slides here. Moving on to the NIRCam portion, I realize I'm down to 1 minute. This is a simulation that Michaela Bagley did for us very deeply as well using Mirage. And the illustration here is just that it shows a comparison between what we'll achieve with W deep compared to what you would get from SEERS. Many of us are involved in SEERS, but clearly it's inadequate for these purposes. One of the galaxies I'll highlight here is shown there in that box. This is a simulated galaxy at redshift 9.7 with a magnitude of 29.3. The top panel here, which has the blue highlighting around it, is what we'll get with W deep compared to what you would get with SEERS. And of course, this then allows you to identify these galaxies very robustly based off Lyman selection type methods. And then we can begin to study those. There are a couple other ones. This allows us, we think, these larger squares here are then going to show a galaxy at redshift 10 and a galaxy at redshift 13, both of which you can detect, but you need this W deep depth of near 30th magnitude to detect them at sufficient signal to noise that you can rule out lower redshift solutions. And that was the motivation for W deep. To illustrate how many of these objects we expect, this is where we're really in terra incognita. We just don't know. The plot shows as a function of redshift, the cosmic star formation rate density we might expect, and there is a range of model prediction here. And the point is they're reasonably well constrained up to redshifts of 8, but then they all diverge going to larger redshift simply because we have no constraints at these places, not with any large statistics. So W deep was built to really answer this question, what's going on at redshift 10, where we expect between 20 and 65 galaxies total in the single pointing, which will then rein in what's going on with the various models. All of these different simulation predictions of different strengths of feedback and star formation efficiency and formation mechanisms, all of which we can begin to test. Possibly we'll even be able to detect a galaxy out of redshift 14, but that's where we just don't know yet. And that's the whole purpose of W deep. So I'll finish here just to give you some summary points, and I'm happy to take questions. So again, WDEEP is designed to be a public, deep survey with both NIRCam and NIRISS in parallel in the Hubble Ultra Deep Field, building off this legacy of the Hubble Space Telescope. The NIRISS component will target primarily feedback, metal enrichment, star formation, and low mass galaxies through cosmic noon, where it leverages off the deepest HST B-band imaging on the sky. I'm quoting some numbers here just in terms of actual depth and the different filters of NIRISS there for people who would like to write that down. For NIRCam, we expect to be able to detect between 20 and 75 galaxies above redshift 10 in large enough samples for the first time that we can study their statistics and their bulk properties. And this, of course, plays into all the aspects of reionization we can imagine here. It will achieve 20-hour depths in sort of central NIRCam filters and 50-hour depths in the J-band imaging and the F444W, and then achieve magnitude depths between 30.5 and 31. And that's the depths we need to detect robustly the strength of alignment break in these redshift 10 galaxies, so we can begin to study them and inform what we want to do in future cycles after that. All right, so I'll stop there and be happy to take more questions. So thanks, Steve.
Thank you, Casey. We will just pause for 15 seconds or so just to give people the opportunity to ask questions, but we'll hopefully have time for one or two questions.
All right, we've got a question on a topic that I know is near and dear to Casey's heart about the Passion Series emission. Do we go red enough to get any Passion Series emission at low redshift? Are there sufficient numbers of low redshift galaxies in the nearest field?
That's a great question. I don't know the statistics. I could dig them up in the proposal. You can dig them out. We will get some. Obviously, they'll all be at the lower redshift end of this sequence, right? For example, so you should be able to detect them out to, well, you have to take the 2.2 microns of the F220W band and then divide by your favorite Passion line. So we'll have them, and they'll be opening up, I think, Passion studies below redshift of 1. Again, it's a single field, so we don't expect that many of those objects. And if you ask me later, I'll be able to dig those numbers out of our proposal, I think.
Thanks for that, Casey. I think while we wait for some more questions to come in, we'll probably move on to Pascal. But Casey, if you don't mind answering any of the questions that pop up, that would be great.
I will be happy to. Thank you.
And Pascal, do you want to share your screen?
All right.
So our next speaker is Pascal Oesch, who's going to tell us about Fresco.
Okay, hello everyone. Yeah, it's really an amazing privilege to be talking to you as one of the PIs of a Cycle 1 James Webb program. And in my case, this is Fresco. This is a 53-hour medium program of NIRCam GRISM spectroscopy at 4 to 5 micron. So Fresco will be conducted by a team of about 25 scientists all around the world, really. You can see their names listed here. We're all experts in galaxy evolution, from imaging and spectroscopy, but especially also we have a strong expertise with HST GRISM spectra, which is going to be important for this program. But really, the Fresco is also intended as a legacy program for the community. We'll be imaging the Candle's deep fields, which are, of course, are really prime extragalactic fields, and the data will be public immediately, so you can play with it as soon as they get off the telescope. And so I'll just show you some of the science that will be enabled by Fresco in this talk today. Just very quickly on one slide on motivation, really for me, the key motivation here is that, well, as you know, with Hubble, we have been collecting huge samples of galaxies in the epoch of ionization, redshift 6 and above, from photometric techniques. However, only a very minor part, 1% only also of the sources at redshift above 6 do have a spectroscopically confirmed redshift. And so this really severely limits our physical interpretation of these sources, right? With photo Z uncertainties reaching up to delta Z of 0.5. I mean, we have limited accuracy with which we can determine physical parameters like stellar masses of these sources. We don't know anything about the 3D distribution of these sources, and we don't know anything about their contaminants in a sense. And so that's really the main motivation. And how can we overcome this? Well, we know that these sources at redshift 7 and above have extreme rest frame optical emission lines. And we know this from Spitzer. If you look at the Spitzer imaging of some of these sources, you can see that they're really booming in IRAC. And it's been known for a while that this can be only explained really if you look at the IRAC colors of sources, redshift 7, redshift 8. They're very different, and you can explain this only through very strong rest frame optical lines, O3 and H beta, that are shifting through these two filters. And so on average, we can determine that these equivalent widths are rest frame 700 angstroms. And as you can imagine, and as you can also see here in this SCD, this really has well, bad implications in the sense that we have large uncertainties on the stellar masses of these sources, even with James Webb imaging in the most extreme cases of a factor 5 to even to 10. But yeah, these lines are extremely strong, as you can also see here in this equivalent width distribution plot. And so we can now, with Fresco, exploit these strong lines and use James Webb's unique spectroscopic window that is being opened up to get an initial line selected galaxy sample during the epoch of reionization and remedy this situation. So how are we going to do this? Well, we're using slitless spectroscopy. So we're using NIRCam, as I said. We're taking a direct image here. This is a simulation that Gabe Bremer did for us from the Hubble Ultra Deep Field. This is the F444W direct image, and then you put in the prism, and as Casey was showing earlier, right, you just essentially smear out this whole image, and you get essentially a spectrum for every single galaxy in the field, but because it's slitless, they're also overlapping. So we will get back to that. But as you zoom in on the trace of a redshift 7 source, you can see here very clearly we will be able to get, so these spectra are of 1600, so you can split the O3 doublet, also H beta, and so we can really unambiguously select these sources through their emission lines, yeah, through these 3 emission lines. H beta here in this case is somewhat faint, of course. And so just to give you an overview of the survey design of Fresco, as I said, we're targeting the Candle's deep areas. So these are the central pointings in Good South and Good North. So we'll be doing 2 × 4 mosaics. So in total, we will get 120 square arc minutes of prism spectroscopy. And so in particular, we're using this F444W filter for 2-hour prism spectra. And as I said, we also need very short direct images to identify the position of these sources. And then the really cool thing about NIRCam is that you can observe in the long wavelength channel, and at the same time, you can observe in the short wavelength channel. And in our case, we're performing imaging in medium band filters, F182M and F210M, so 1.8 and 1.2 micron. And that really extends the Candle's data that is available already in these fields from HSV and also complements the GTO JADE's data. So in terms of depth with the F444W prism spectra, we will cover 3.9 to 4.9 micron with a line sensitivity of about 3 × 10⁻18 ergs per second per centimeter squared at 6 sigma. And so we expect to detect essentially the O35007 flux for sources about 1 magnitude below L star. Then in terms of imaging sensitivity, we will expect a 28.5 sigma for a point source in the medium bands, and as I said, relatively shallow in 444W. And so in total, this survey requires 53 hours, again, medium program with 36 hours of science time. And again, important, the data are public immediately. So you can expect, we have observing windows between October, December for Good South and January, April for Good North. And the actual orientation of these pointings will also depend a bit on the scheduling. Just a quick word on advantages and disadvantages of slitless spectroscopy. As you've seen, right, we obtain a spectrum of every single source in the field, which is great because it allows us to get a complete emission line selected galaxy sample, which really is impossible to achieve with NIRSpec, both because you have to pre-select sources, but also because of the fixed grid of the MSA. And then we will obtain total emission line fluxes. So we will be able to get slit loss calibrations for MSA spectra from our data in the same field. But the main problem here, of course, is that we really do need to model the spectrum of every single source in the field to be able to clean for contamination. And because of the very large overheads, we are only taking one orientation. However, we can build on our extensive experience with HSD GRISM surveys, like 3D HSD, for instance, and in particular, we will be building on this amazing software tool that Kate Bremer has written, Grizzly, that is really built for space-based slitless spectroscopy. And you can find this on GitHub already. And so what's the science that this data will enable for the epoch of ionization, which is, again, important for the conference here. You can see here on the left, we will be able to really get spectroscopic redshifts for a large number of sources at high redshift. So we expect about 330 spectroscopic redshifts from redshift 7 to 9. You can see down to the absolute magnitude limit that we expect this. And even at lower redshift, we expect about 1200 redshifts from redshift 5 to 6.5 through the H alpha line, for instance. And so this will allow us to really probe the 3D, the small scale clustering of sources, and really the buildup of the galaxy population and ionized bubbles and so on in these two fields. Then on the other hand, we will get these terrestrial optical spectra for sources. These terrestrial optical emission lines that we can then really, on a source by source basis, subtract these emission lines from the broadband photometry. Here this is Spitzer photometry in this case, but really get accurate stellar masses for every single galaxy in this field. And so this will enable UV luminosity functions from spectroscopic samples, accurate stellar mass functions, as I said, but it will also allow us to get the 3D clustering as well as ionizing conditions in these early sources and much more. With our 4 to 5 micron spectra, we will not only be able to target high redshift emission lines, but also the Paschen lines that were just asked about earlier, in particular Paschen alpha and Paschen beta, between redshift 1.5 and about 3. And so those will be dust and sensitive probes, of course, of star formation. And here's a simulation again of a source in the Hubble ultra deep field, redshift 1.5. Again, if we zoom in on this source, we can directly get an emission line map, the Paschen alpha map. And so really that gives us the spatial distribution of star formation. And again, in terms of science, we can really probe that we get dust insensitive probes of inside out versus outside in growth of galaxies really across cosmic history, because of course we can also do this with H alpha and at higher redshift as well. Then just a quick word on the imaging. We will, as I said, we get these medium band images here around 1.8 and 2.1 micron, and that really extends what is available in these fields with Hubble. So essentially everything, all the science that can be done with Hubble, we can extend to slightly higher redshift. In particular, Balmer break studies, also identifying quiescent galaxies in these fields up to higher redshift. But also we get UV continuum slope estimates directly for the sources for which we will get redshifts from the GRISM spectra. And so just the data products to finish up. Again, we'll be following the very successful data release model of the 3D HSD survey. So you can expect to get 2D, 1D calibrated spectra, of course, catalogs of redshifts, but also emission line measurements, the 2D emission line maps for sources that are well detected, and of course, these near-cam images that are aligned and calibrated to the candle's deep data, in particular the medium band filters. And finally, we will also provide photometric catalogs that include physical parameters that are derived after correcting for this emission line contamination. And importantly, I think we will also really be able to provide statistical correction factors for emission line contamination in broadband photometry that can be used in other surveys that are being conducted with James Webb all over here. And so this I just leave up my summary of FRESCO. Again, it's a near-cam GRISM survey, and you can get news in this webpage that is still under construction. Thank you very much.
Thank you very much, Pascal. I can see there's a couple of questions already in the Slack, but we'll give people 30 seconds or so just to add some extra ones. Oh, just while waiting for a couple of extra questions, when people are interacting via Slack, we kind of think it's a good idea whether people can rename themselves with their full name but also the institution, perhaps your pronouns, and also your career stage, just to help with your interactions between researchers at different levels. So I think if you should be able to see a few of the SOC have adopted this already, which I think that would be really useful. Steve, do you want to ask the first question?
Yeah, Pascal. So the first question is, what could we learn from stacking the spectra of the high redshift galaxies? Could we measure metallicities at redshift greater than 7?
That's, yeah, very good question. That's definitely something we would like to do. We will get H alpha here and then 2 as well, of course, for redshift 5 to 6.5 redshifts. Well, in principle, unfortunately, we only have this very limited window, right, of from 4 to 5 micron. So in most cases, we only get the one line, but definitely we will be trying to model this, also the O3 and H beta lines, and hopefully get some information about the metallicity buildup as well.
Thanks, Pascal. Another question asks, how much of a gain would you make by adding a second orientation, perhaps in cycle 2? Presumably it wouldn't just be kind of doubling the amount of data you've got, because it hopefully makes subtraction. Sorry, I'm kind of paraphrasing this to add a bit more detail.
Yeah. No, I mean, the problem is really with the overheads. So essentially, if we added the second orientation, we would have added essentially 15 hours of overheads without any gain in sensitivity, right? And the main problem is what you see here, right? With 3D HSD, for instance, we also have only one orientation. We have to model all the spectra, and it's really only kind of a gain is only in systematics in a sense. And if you're really interested in one particular galaxy, then a different orientation might be very useful. But in a statistical sense, I think we will have a good handle on these sources, and we will be able to subtract and model the contamination quite well, I think.
Thanks, Pascal.
I'll ask one more brief one, if that's okay. So a couple different versions of this question, but do you expect line emitters that lack continuum detection either in the existing HST imaging or in your direct imaging, or presumably in the JADES imaging in the field?
Yeah, that's a very good question. We don't know. Let me go back to the equivalent with distribution plot from Ryan here. We don't know what's going on up here, right, at the very high end of this O3 and H beta equivalent with distribution plot. But at least for a source that has an average terrestrial optical equivalent wave of about 700 angstroms, we specifically designed our pre-imaging, which is really shallow, right, to be able to detect every single source that has an O3 and H beta line. But indeed, there may be sources out there that with much stronger lines that we will have to hunt out, maybe in the JADES data when they become public.
Thank you very much, Pascal. So if we can now move on to, I think it's Ivo, sorry. Ivo, are you there?
I am.
Excellent. Do you want to share your screen? I assume it's some horrible time in the morning for you, Ivo.
Yeah, it's about 12:30.
Apologies.
All good. All right. This is working?
It's just coming up for me, I think.
Yeah, so the connection will be a little slow because, I'm from far away. So can you see my screen?
Yeah, I can see it now.
All right. Can I start?
Yep, go ahead, Ivo.
Okay, great. Well, first of all, thank the organizers for inviting me and having this very exciting and dedicated session to JWST. We've been talking about this for so long and been looking forward to it. This is so amazing that's going to happen. So I'd like to acknowledge my collaborators as well here. So it's for many years we've been wondering and fantasizing about this and working on this. It's with a wonderful team of people. So it's really a pleasure to be here and to present these. So the science questions that we'd like to address with Uncover is the emergence of the first galaxies during the Dark Ages. And you've noticed that all the pundits always put the first galaxies in quotes. So for the purpose of this talk, it's simply galaxies at very early times. We'd like to know whether galaxies reionized the universe. So this hopefully is something that we can contribute to with the observations in Uncover. There's a bunch of legacy investigations that can be done with these data, in particular on stellar mass complete studies to redshift up to 10. And just to put this program into context, assisted by gravitational lensing, these will be some of the deepest imaging and spectroscopy being delivered by JW in cycle 1. So why do we need to go very deep? So one of the main challenges, if you want to go all the way to redshift 12 or 14, is galaxies become incredibly faint. So unassisted by lensing, you have to go to 31st or 32nd magnitudes. And even with JW, that's going to be very hard. You need to have very, very long integration times, so like tens of hours or so. And so here you can see the gray area. It is just a plot of the numbers of galaxies you might expect versus limiting depth for some fiducial luminosity function. And so the gray area is the area that you would need to do to have more than one galaxy in your field. And so you see that up to AB of 30 of magnitude or so to redshift 10, it doesn't make a huge difference. So the numbers of galaxies, it may be a factor of 2 or so. But as you start to probe to redshift 12 or 14 or 16, the difference becomes an order of magnitude. So to get proper statistics at redshift beyond 12, currently with the integration time that we're looking at, you need to look into lensing fields. Exploring the Dark Ages, that's clearly sort of depth limited. And another area where we're lacking in depth is the faint end of the luminosity function during the era of reionization. So we really like to have a better understanding of what the luminosity function is doing at the very faint end, but also to have spectroscopic observations of the very faintest galaxies, which we think dominate the UV luminosity budget, and also the ionizing photon budget. So this has been probed until now with HST, but it requires extreme lensing, orders of at least a factor of 10 or more. And so what we'd really like to do is, with better statistics and with less dependence on systematics, probe this very faint end of the luminosity function, at -15 or so. And so that requires simply deeper data, which can now be delivered with James Webb. And in addition, we'd like to spectroscopically observe these galaxies and look at their emission line ratios and the stellar populations, and in particular the ionizing photon production. So that's the premise of Uncover. So we're going to do very deep NIRCam imaging and NIRSpec prism spectroscopy in a gravitational lensing field. So this is a cycle 1 Treasury proposal. It's about 50 hours of primary observations, 50 hours of parallel, mostly imaging, 70 hours wall clock. All of the imaging and spectroscopy will be immediately public. So that's important to realize. It's really meant to invite everyone to participate in this very exciting science. This is why JW was built, and so we are very happy that these are the types of data that will be available to everyone. The field is going to be the Hubble Frontier Field, Able 2744. It's a low infrared background field with good visibility, accessible from the south with ALMA. And of course, it has a very extended high magnification map, so assisted by strong gravitational lensing. The basic setup of the program is that we're going to split the observations in 2 epochs. Early in the cycle, we'll do a deep NIRCam imaging map, 4 to 6 hours per filter. And it's a map that will cover 25 square minutes. So it's a 2x1 map, filling in the gaps. And so the filters are shown here. These are all the broadband filters in the short wavelength and long wavelength channel, adding the 410 medium band filter to be more sensitive to strong emission lines, which can bias stellar masses. So we reach about 30 AB magnitudes, and this will reach to up to 32nd AB magnitudes with lensing over small areas. There will be additional 20 arc minutes or so in the parallels, both by NIRIS and with NIRCam. And so this will provide extra samples of high redshift galaxies that we can follow up with spectroscopy in future cycles. So the hope is that we will have photometry for about 4,000 galaxies beyond redshift 6 and at least 100 beyond redshift 10. So the second part of the observations later in cycle 1, so 6 months later, will be very deep NIRSpec prism spectroscopy on the NIRCam selected sample of the first half of the cycle. So these will be NIRCam, very deep, selected, and it will be 20 hours or so of spectroscopy in prism mode. So we get the full range from 0.6 to 5.3 micron, which is perfect for not only exploring, if you find new objects that have very unusual SED properties, you can now get a full spectrum of it. But you also are sensitive both to emission lines, and you can get redshifts for sources that have no emission lines. So this is great for very high redshift galaxies where we might not expect strong Lyman alpha, but we can still measure a redshift down to 29 AB just from the continuum break alone, from the Lyman break. This is also great for very faint dusty galaxies and quiescent galaxies where we might not see very strong lines. We expect up to 20 hours per target, and in our current designs, we expect spectra for about 500 galaxies. So you might recognize the field as a field that is also going to be observed by the ERS program, by the GLASS, as PI by Tommaso Traio, and they are going to do very, very deep high-resolution spectroscopy on HST selected galaxies, as well as NIRIS slitless spectroscopy. And so where Uncover is different, and so what it adds to what's already available, is that it will provide NIRCam imaging on, so much deeper than the HST and Spitzer data available, 1.5 to 3 magnitudes deeper, but also it's going to be over a much more extended area because the current HST is focused on the southwest core of Able 2744, and Able 2744 is kind of a bit of a freak cluster, as I will show in a second. And in addition, we'll do R of hundreds spectroscopy, which will be very sensitive in the continuum. So this is a lensing map of the Able 2744, and shown here is the familiar magnification map of the Hubble frontier field area. So it's 1 arc minute on the side. And here you can see that the extended lensing map is extends, over a much larger area, about 20 or 25 arc minute squared, which can be covered with a NIRCam map. And so this is the area that has more than a factor of 2 magnification. So it's going to provide us much better samples. So the science is first galaxies. So owing to this increase in depth and area, we now have good statistics to redshift 12 to 14. So this allows us to differentiate between models of early star formation, fast or slow evolution, depending on the star formation efficiency. But we'll also, for the first time, be able to spectroscopically confirm these galaxies right in cycle 1. And estimate their stellar properties, their spectral properties, their emission lines, and continuum breaks. The second science topic is the properties of faint reionization area galaxies. So the hope is that with the deeper data, we're less reliant on extreme lensing. So we're more in the moderate lensing regime between a factor of several and a factor of 10. So there's not as strong dependence on systematics, simply by going deeper over a wider area. But we're also getting spectroscopy for the most highly lensed galaxies. So for the sum of the galaxies that have magnifications of 10 or more, we'll get really good high quality spectroscopy. And so we'll measure strong lines for the entire suite between O2 and S2. We're going to be able to model and put constraints on the ionizing photon production efficiency, but also get indirect constraints on the escape fractions from line ratios and equivalent widths. And there's a bunch of legacy science that can be done. We're probing the very, very faintest end down to 10 to the 8 or 10 to the 7 in stellar mass. And this is complementary to the surveys that are done, as we've heard before, on wider fields, for example, in Cosmos, and with the ERS data. And so put together, you'll find that these will have a good constraint on the shape of the stellar mass function, from which we can, see the mass growth of stellar mass in the universe and get estimates on the star formation efficiency even at earlier times. So the key difference here to the HST studies is that these are stellar mass complete studies because they will be selected in the F444 filter, so in the rest frame optical. A stellar mass complete in this sense means that we're going to be able to detect galaxies with high mass to light ratios. So quenched galaxies, dusty galaxies. In essence, the uncover will tell us what the universe will look like at the very low mass end. If there's like 10 to the 9 solar mass galaxies that are quenched out to redshift 9, we should see them. The same thing with dusty galaxies. The importance of dust is very poorly understood beyond redshift 4 due to sensitivity limits, and we'll be able to detect dusty galaxies, highly obscured galaxies, should yet exist, all the way to redshift 9. Uncover will produce several data products. We'll produce reduced imaging of all the cluster, so the primary NIRCam data on the cluster and on the parallel data off cluster. We'll provide a multi-wavelength photometric catalogs, fits of stellar population properties, 1D reduced spectra, spectroscopic redshifts, a joint multi-wavelength photometric and spectroscopic catalog, and a data explorer. So that's the summary. It's a very exciting program, I think. I hope you think so too. It's going to be extremely deep in a strong lensing field, both imaging and spectroscopy on NIRCam selected galaxies. Our science teams are first galaxies, reionization, and mass complete studies, and we'll be providing a bunch of data products for the community on a fairly rapid timescale. Thanks.
Thank you very much, Ivo. I think we don't quite have time to ask any questions, but there are a few on Slack right now. So I think there's 3 questions on Slack. So if you don't mind answering those either now or when you wake up in the morning, that would be fantastic.
Yeah, sure.
Okay, so in the interests of time, yeah, thanks, Matt.
Okay. So can you see the first blue slide there?
That's right, we can see and hear you, Matt. So our next speaker, our final speaker of this half of the session, and then we'll have a 45-minute break. Our final speaker is Matt Malkin, who is going to talk about Passage. And take it ahead, Matt.
Thanks. Last speaker in between you and your coffee. Greetings from UCLA. I don't think I have to convince anybody now, if you've been listening to the previous talks, that if you want to understand high redshifts and the era of recombination, you just cannot do this without spectroscopy. We're talking about in the infrared. And you also realize if you want to do a survey with JW, you have to take advantage of its unique capability for slitless spectroscopy. So you get all of the spectra of everything in the field in one shot. Can never be done from the ground, ever, because of the air glow of the atmosphere. So this was all known. To show an introductory slide about the background, what was previously done. There's not much to show you. The idea of slitless spectroscopy was, of course, pioneered with the Wide-Field Camera 3 on Hubble Space Telescope, but in all honesty, trying to go for high redshift, for example, Lyman alpha emitters, was just at the limit of what you could do. Now, one thing that, even if you're sold about, yes, infrared slitless spectroscopy from space, you got all of that, what you might not be sold on is, let's do this without any JWST observing time, because that's too valuable to take. Of course, you should. I'm just kidding a little bit, but the telescope and the NIRISS instrument was really designed with a lot of thought put into how you could do pure parallel infrared slitless spectroscopy, as we, the WISP team had done with WIFC3, WISP being an acronym of acronyms, WIFC3 infrared spectroscopic parallels. This is about as far as WISP was able to get with a few galaxies with Lyman alpha emission it's interesting, up to about redshift to 6.4, even though it was more sensitive at higher redshift, did not find anything. We just don't know what the high luminosity tail of this luminosity function is. But anyway, who cares whatever's been done? I mean, JWST with NIRISS is such a ridiculous game changer that honestly, all bets are off. Now, it appears that you cannot have a project here without a good acronym. We've struggled with that a lot. An acronym that is not itself made up of acronyms. So here's our best attempt. So PASSAGE, in case y'all don't remember, stands for Parallel Application of Slitless Spectroscopy to Analyze Galaxy Evolution. The important point is parallel slitless spectroscopy. And so you can see the picture here from one of our team meetings. And we're trying to navigate this, this passage. On the one side, we don't want to bump into the rocks of not having enough sensitivity to do this project. On the other hand, we don't want to bump into the rocks of not covering enough fields. And we're trying to thread the needle with this Pure Parallels project. And well, as you probably realize, when you're doing spectroscopy infrared, there are many, many science goals far beyond what this team anticipates doing. And the goals that took most of the proposal, or the more pages, were actually the so-called intermediate redshift of 3 and 4 galaxy science with emission lines and absorption lines. But there was a section which I think a lot of people liked about end of recombination, well, era of recombination galaxies, particularly looking for Lyman alpha and Lyman breaks spectroscopically at redshifts 7 and up. And just want to put the names on here. You know a lot of these people, but what you might not realize is, I mean, these are some of the most friendly and collaborative people you're just going to find anywhere. Man, if I were a young person right now, if I were a middle-aged person, anything kind of person here, I would really get in touch with any of these people. The chances are very strong that you've got a great idea here that this team of good folks is not going to be able to pursue with this project. And we'd love to talk with you about it. I think it would be very productive. I mean, I'll be disappointed if most of the science that comes from PASSAGE is done by these team members. That's not what's going to happen. Actually, it's going to be you folks. So obviously you want to detect Lyman alpha emission. And so we've really tailored or torqued the program to emphasize that by putting most of the entire exposure time is into the shorter wavelength F115 grism specifically for that purpose. And so this is the kind of sensitivity that you can get when you put most of the time into this 115 grism, from 1 micron to 1.3. And even in Lyman alpha emissions, well, even if there's no continuum there at all, we feel like we can get down, or if there's a lot of continuum, we feel like we can get down to pretty sensitive levels, at least for the brighter Lyman alpha emitters in these randomly selected fields. And so there's a few specs. It's also very important that we're spending additional time in each of these visits getting the supporting imaging in each of those 3 bands. So we should have detections for everything in the broadband filters, unless it has a very, very high equivalent width, but we're looking for those as well. And this is rather important, we'll have the continuous spectral coverage all the way out to 2.25 microns. Of course, it's for a lot of other science purposes, so that we can separate out and distinguish the true high redshift galaxies from the intermediate redshift interloper galaxies. So what was mentioned actually briefly, people might not appreciate, we don't actually need emission lines here to do interesting things. These are some simulations of some of the, well, sort of a typical field at 26.6 magnitude and a deeper field at 27 magnitude. And we believe that not only can we detect the break at the Lyman limit, for example, at a redshift 8 star-forming galaxy, and just then we can distinguish it, for example, from a redshift 2 interloper. There's a bomber break there where you actually detect emission lines and you detect continuum. Even a quiescent galaxy that's an interloper, we detect the continuum beyond the Lyman break, proving that it's not a Lyman break galaxy. And the PDFs of the redshifts say that this is going to work, at least for the brighter, very high redshift galaxies. This is an estimate from Alexa Morales about what emission line, that is Lyman alpha galaxies, will be detected here. Now, this is not exactly what we ended up with in the final passage parallels. It's a little bit of guesswork as to how many pure parallels we could get. We were very conservative, very cautious about this. We're only looking at the parallels that are done with NIRCam and MIRI as the primary instrument. I think we'll go deeper than this because we're spending a lot more than 2 hours. In fact, we don't even get started on the Lyman alpha search until we're spending several hours on it. But, and I don't know how many fields we're going to get. We're still in communication. The big question is not, there's just tons of pure parallel opportunities. The big question is how many calibration fields or frames will the Institute decide to take. But anyway, we really have the sensitivity, of course, depending on how many Lyman alpha emitters there are at redshifts 8, 9, and 10, to have reasonable samples. And the particularly strong selling point here is that these are going to be in dozens, maybe if we're lucky, 40 or something fields all over the sky randomly, because we're very, very concerned, and you've seen why, about the cosmic variance of the EOR galaxies and Lyman alpha emitters and so on. So the estimates, well, you can take these with a grain of salt. They're very uncertain, but I think we're going to have dozens, maybe 60 Lyman alpha emitters above a redshift of 7, and you get the imaging, and you get a lot of other things you'd like to know as well, far UV slopes. One thing we're very excited about is getting some of the other metal emission lines at longer wavelengths at the same time. And of course, those can be gotten even at redshifts approaching the era of recombination, redshifts of 5 and 6 and so on, which we're interested in that as well. And then finally, I just said this actually, but to remind you, of course, we feel that we're entirely complementary to the deep surveys that are just going to do brilliant work on relatively small fields in one place. And you can see it's a little bit of a matter of luck. You've seen a lot of these simulations, whether those fields will hit relatively neutral and rather opaque regions of the IGM, or whether you might get lucky and fall in one of these regions with a lot of UV bright sources, which will have opened up ionized bubbles, in which case we'll see lots and lots of Lyman alpha emitters, those gray objects that we're looking for here. Let's see. So that, I'm sorry, I went a little bit quick over this, but that in an overview is what we're trying to do. So I guess I'll just go back to my first point again. Please do be in touch. Oh, there's one more point here. We've gone to a lot of trouble in the proposal to say just how hard we're going to work on releasing data as fast as we can and as completely as we can to the community. That's really our main goal, as I said here, no proprietary period on these pure parallels. So we'll almost immediately reduce and release images and spectra, 1D spectra, but we're also planning, now of course this depends on whether we get our modest funding request approved for this. It's in the proposal. We want to do high-level science product releases. For example, metallicity determination, not just redshift determinations, line flux and so on, but metallicity from line ratio maps of resolved galaxies. That's something we'd like to provide to the community. To give you an example of how seriously we want to do this. There are many other related projects for people who are interested in reionization. We want to look at leakage of Lyman continuum photons. We're interested, of course, in magnesium-2 emission lines at more intermediate redshifts as a proxy for leaking Lyman continuum emission. And obviously, if for every Lyman alpha emitter that we can get our hands on, we want to look at the spatial extent of the Lyman alpha. You know, with JWST, we're not assuming that everything is a point source. I'm not sure there's going to be all that many point sources left after JWST, you know, gets a hold of these deep observations with this incredible resolution. One other thing I just wanted to mention, because it came up in the chat, we're planning for every one of these fields to have orthogonal orientations of the grism. So we'll have half the data with the spectra running this way, and some of the spectra will be on top of each other. We know that. We have tools that we're going to try to decontaminate them. It's tricky. I think we'll be able to, actually. But we'll then also, for those ones that are hopelessly contaminated, we'll have the orthogonal orientation of the grism to see which emission lines are coming from which object. I think we're really in pretty good shape on that. Quite a lot of attention is being given to that. So does that leave time for questions?
Yeah, thanks, Mark. I think we've got just a minute or two for some questions, and I know there's some questions in the chat. So Steve, do you want to ask the first?
Consider strategies to address possible differential magnification. What a cool idea. In case the emission lines of the continuum are spatial, so I love that. Yeah, we've been discussing this quite a bit at JWST resolution. You cannot assume, in fact, this is a very crucial science question, that you want to extract your spectrum of your emission line with exactly the same aperture that you determine from the broadband continuum. So we've got the tools to do that. That might not be in the first data releases. In other words, you have to get into the data to try to decide where the centroid of the emission line, or what the distribution emission line gas is. But so the data are definitely going to be provided. What we're trying to do basically is to provide fully reduced and calibrated data cubes. So anybody will be able to come in and say, okay, including us, of course, we want to make emission line maps and compare them to the possibly different maps of the starlight in resolved galaxies. Now, we didn't go on about that at very high redshifts too much, but it could be an effect there. Certainly going to be a very important effect for all of our redshift 2 and 3 galaxies. So yes, very good question.
And Matt, I'll ask you. I'm sorry, Steve.
No, go ahead.
All right, I'll ask you another question. Are peer parallel surveys biased by the fact that overdense regions may be targeted preferentially in the primary field?
Very good question. By the way, I did want to point out about bias. We're not doing any photometric reselection. We want to know, for example, the true distribution of Lyman alpha emitters in the sky without any photometric reselection. But an interesting point, we're at high latitude fields, not in the galactic plane. I don't know. There's a lot of observations of people. We've gone through all of the GTO observations. A lot of people are doing stuff like exoplanets and stuff like that. I guess people are interested in that. So it's not as biased as you might think that will be. Yes, there's a few famous fields. Of course, many of the famous fields, they've already took their parallel observations and incorporated them into attached to the primary. So we'll look at that. Of course, we can go back, if we really do have 40 or 45 fields, we can go back and construct less, basically unbiased samples that were not chosen because it's near a famous deep field. But there's a lot less of that than you would think, actually. Darn good question, Matt.
Thanks for that, Matt. There is a few more questions in the Slack, which I've just tagged you on. If you don't mind answering those in the Slack later, that'd be great. So that brings us to the end of the first half of today's session. So what we now have is a 45-minute break or a 43-minute break. Now, many of you will just want to get away from your screen. That's always a good thing to do. But for those of you who want to try and chat with people, we're going to trial the service called WonderMe. So there is a link to our WonderMe room, which is in the general channel on the Slack. I'll just ask Will, can you post it into Zoom as well. What I'm going to try and do very quickly is just do a little demonstration myself live by sharing my screen. This could go horribly wrong, but let's see.
Steve, can I mention one thing before you do that in case we lose people?
Of course.
Yeah, I just wanted to ask that the speakers for session 1B try and come back in around 30 minutes, and we'll make sure you're all in the right place and test your screens and all of that. All right, that's all.
Great, thanks, Steve. So I'm hopefully now sharing my screen with what we can see in WonderMe. One of the downsides of this service is that I don't think it works on Safari. So if you're a Mac user, you've got to try something else. But what you can see here is, you can see my avatar is down there. I think I can zoom in a little bit and you can see people moving around me. So I can move around like this and I can go try and find Will, if it stays still. And this will hopefully put us both in a little bubble now. Oh. So hopefully, Will, can you see me? Oh, there we go.
Yeah, and we can create a horrible echo.
Yep. So let me turn off the mic there, but you can see that two people can get together into this little room. And if somebody else wants to join us, if there's anybody else around, you can come into our little room now and move around. But you see that we've also made these extra little rooms where you might want to talk about specific topics for now. Oops, Will has left me. So we can both go into the AGN room, for example, and meet up. And again, we're back there now. So do encourage people to have a play around. Obviously, do try and have a screen break as well. That's always important. But this is the reason why we've kind of given ourselves a good kind of, well, 40 minutes from now so we can do this. But yeah, we're very new to this service as well. So yeah, please forgive us, but come and say hello. And yeah, hopefully see everybody else back in about 40 minutes. Great. And thanks everybody for joining this morning. Sorry, this afternoon for me.